August. Okay. Welcome back, everyone. Was traveling quite a bit actually. It's like four corners of US. But I'm back. And looking forward to continue the lectures. Hopefully the Monday lecture was good and you guys learn new things. Fatima is a great lecturer and she does work on this topic, so she's quite knowledgeable. All right. So last time we talked about cache side channel attacks. Now we're going to talk about cache side channel defense. So it's important to note that, you know, for every attack, there should be also defense. And of course, defense is significantly more difficult than attack, unfortunately, because defense is essentially requires you to kind of close all the, let me full screen this. Defense requires you to kind of close all the channels versus attacks is kind of like you show it for like one tiny bit of one particular system. And if it's successful, then the attack considers success. But if your defense sometimes work and sometimes doesn't work, it doesn't consider as a success, unfortunately, especially if your researcher tries to publish papers, attacks papers like publish instantly versus defense papers takes a lot of iterations, unfortunately. But the more important things, of course, is from the designer's perspective, from user's perspective, is defense, right? Nobody cares about whether or not you're coming up with a new attack. The attacks is generally just there to show the vulnerability, to educate the public about the problems, and then hopefully we can come up with good defense. Another thing about defense is that unfortunately, defense usually comes with a cost. It's really hard to have some form of a defense that doesn't impact anything else. So you have to accept the fact that defense comes with some cost, typically in forms of extra hardware or software, which you then translate into extra power overhead or area overhead. Of course, it requires some design time. And so there's all sorts of costs that comes with the defense that one has to also consider. With that in mind, we're going to then start talking about defenses. Any questions before we get started? All right. So I want to kind of like, you know, do a little bit overview of the general status of attacks and defenses in architecture, computer architecture, and generally in hardware systems before actually jumping to the specifics of defenses for cache side channel. So essentially what we are observing right now, this is kind of like also I talked about it in the first lecture, is we're kind of observing two important trends. The first trend is we're gonna see more and more devices being used. This is typically referred to as Industry 4.0. This is the fourth revolution this is fourth industrial revolution. For those of you interested in like whatever the first three was like, the engines, the turbine engines, and then the robotics, and then the second one, I think electricity. I don't know, I have to check, but this like in 80s, in 18th century and 19th century, basically. And we are observing, basically, we are witnessing the Industry 4.0 revolution, which is the revolution of cyber physical systems, that everything is being automated. And we're kind of like now is 4.5 or something, but with now machine learning is also integrated into it. But generally what we're seeing is that more and more devices are becoming integrated in our lives, right? So and that's an important aspect in terms of security, because as you have more devices controlling more things, then of course you're opening up to more attacks. And number two is that now these devices are now controlling more security critical applications. In the past, used to do a lot of things manually or in the analog domain, but now we're moving everything into some form of a digital. As a result, these two things together, plus it results into that it's generally more difficult to secure computing systems. Another important thing that we probably know about, and I want to kind of like emphasize here, is that we are also observing a shift in the computing paradigm. Of course, 20, 30 years ago, the computers wasn't even that widespread, but now once it became widespread, it was mainly local computing. So everything was kind of local on the machine, and then you kind of like exactly who is using it, who is installing what software in it, and all that. Then the internet came, and you kind of will start sharing things, but you never share like computation tasks. You mainly share like the outcome of the task to each other. But what we are observing now is more of like a remote computations, right? So you have two extremes of like, you have end devices or smart devices. Most of the computation task is not done in some form of a cloud environment. So we are kind of shifting from what we used to be a local and secure to something that is more of remote and as a result hostile. Why is it hostile? It's mainly because it's essentially this sharing allows attackers to use new opportunities to launch attacks, particularly side channel attacks, as you've learned last time, because essentially this kind of co-location of applications allows the user, essentially the attacker in this case, to exploit and launch some attacks. And there's also, since these devices are kind of like more in the hostile environments, in the public environments, then there's also opportunity for physical attacks to the systems. This is not something that we're going to talk about in this course. Those of you who took my the other course, we mainly talk about that. But essentially what is happening is that, it allows the users, in this case, again, adversaries to attack the system. So as I said, mainly what we are focusing on, and the main reason that, attacks like cache side channels are very important is that tasks are being implemented in this cloud environments, and the attackers and the victim are kind of co-located on physical hardware in this cloud environments, and gives the opportunity for the attacker to kind of look at this different patterns. And as you've seen before in the previous lecture, one example of it was cache, and we showed you a bunch of different types of cache side channel attacks, but unfortunately, it's not just limited to cache. It's actually all over different components of the system, including the memory and the network and the processor itself and different components within the processor and all that. There's like a huge amount of papers, attack papers in the past like 5 to 6 years, just basically trying to attack every aspects of a computer system, and show that almost all of them are is quite possible. All right. So, and then what is the fundamental reason that side channels are important? Again, the lecture on Monday kind of touched this part. But that generally the reason that side channels itself is an important problem is that there is this unintentional or intentional correlation between the signals, the side channel signals. So that'll be like, cache, patterns, could be power consumptions, could be any other types of side channels. And the applications and the data on that applications is being executed, right? If there weren't any sort of correlation between them, then measuring these patterns doesn't matter, right? Because you're just essentially seeing some signals that has nothing to do with what exactly being happening on the system. But unfortunately, since there is a very strong correlation between the applications and more importantly, the data that being used by that application and these signals, that's why the attacks and the side channel attacks are like very, very important. To kind of like, before jumping again into cache side channel attacks, particularly just a general background, and again, probably you've seen this on the Monday's lecture, that there are two classes of side channels. There's what we call digital or microarchitectural, and the other one is analog or physical. The analog physical ones are those that are obviously analog signals. These are signals that one can measure from some distance. And these are different physical properties of the system, such as power or the temperature, or even sound, or even electromagnetics. These are physical because there are some physical signals that one can actually measure. You use sophisticated, physical equipments to measure these signals. But typically, this analog one, you can measure it from some distance, so even outside the system. So you don't need to be physically co-located as one process to the system. You can actually measure it from some distance, depending on how far these signals can reach. Typically, they are very weak, so you cannot like measure it from kilometers away or miles away. But like maybe within this room, I can measure things from, let's say, the computers in the back and so on and so forth. So there are lots of attacks that way. Interesting thing about these analog side channels is that all of the defenses that we kind of provide for digital, like for example, cache and all, won't be directly applicable, unfortunately, won't mitigate the analog side channel in most cases, mainly because that, essentially the assumption here on the analog side is that the attacker is not even on the same machine with the defender or with the victim. Versus here, the main solution, as we're going to talk about, is essentially you don't want to co-locate sensitive information with non-sensitive information. If you can do that, then you're kind of good. But there, that's not the case. You just need to somehow make it impossible for the attacker to measure your signals, which typically much harder because you require some form of a physical shield and all, which is more difficult than say that, okay, I don't run another process in this system. Another difference between digital and analog is since digital is basically based on co-location, it can run on the cloud, right? So you can actually attack a cloud environment with digital, but with analog, it's very unlikely that you run it on some form of a cloud because essentially the idea here is that the attacker needs to be close to the server, which most of these servers are actually secured, physically secured in some rural environments, and nobody can go inside the server room unless they have proper authorization and so on and so forth. But this is typically much, much more difficult to launch. Although there are some interesting attacks that tries to kind of bridge the gap between these. So essentially there are digital attacks that tries to read some form of a physical sensor on the device. So there are actually some attacks that shows that one can, for example, hack into this power sensor of a device and then read it through some other process. So that way you can actually have both ways, which is also quite interesting types of attacks.
Did time fall into one of the particular categories? Fatima was telling us that it was kind of vague.
Yes, so time is essentially kind of a means for both of these to be measured. So you can time, for example, various events in the cache, and that leads into an information. You can also time, for example, different events in the power side. On the time is kind of like all of these essentially translate into a timing side channel. So it's really when we're saying digital marker architecture, really what we're measuring is kind of some form of a time, but not necessarily. Sometimes you're also like measuring some events. So yeah, it's kind of either or. Sometimes you can put it into that category. Sometimes you can put it in this category. All right. So with that in mind, let's actually talk about defenses. For defenses, we need to first answer this fundamental question that how do we enforce security in our computers today, right? There are three kind of main principles that we follow. The first principle is that we do what we call principle of least privilege. All of our computer systems tries to have at least multiple privilege levels. If there is some form of an operating system that you typically at least have like, a user level and a root level or a system level. The user level can access some things, but they cannot access many things. So control of the hardware and assigning tasks and controlling memory and all that is usually done by the root level, and the user level can only run particular applications. And then, as I said, there is like a very important aspect and notion called privilege separations that typically gives at least two levels. In some cases, there are three, or some cases even there are four protection layers or levels. How do we actually achieve this? We typically achieve this through some form of a hardware support. So you can think about it as, different processes tries to access different part of the memory. And essentially the hardware kind of like looks through the privileges of this and say that, okay, you can access this part, but you cannot access this part, and so on and so forth. So there is some form of a simple access control, the same way that you can think about that we do access control for people. Hardware also do access control for the process. So everything has a process ID. Every request is tagged with that process ID, and then hardware basically decides who has access to what. This is very important aspects of the things. The second thing is that it's kind of relevant to the same thing as this is the notion of isolation. So we definitely need isolation across processes. Sometimes you also need isolations between different privilege levels, and even within the same privilege level, we need isolation. Isolation in terms of computer systems is mainly that contents of the memory, both read and write, not just writes, both read and writes, needs to be only accessible to the particular process. Typically, root process read access, or sometimes write access to all the processes, but different user level processes should not be able to read each other's memory. If they do, then the whole thing is broken. The last thing is what we call a trusted computing base, or TCB. Essentially is that all of our computer systems based on this fact that we start the trust from somewhere and then build the trust on top of it. So there's this notion of bootstrapping the trust. Usually that's kind of simple thing is we call it like TPM, or trusted platform module, which is a hardware unit. How do we trust that? We have some standards, we have some even cryptography methods to kind of verify that. And the idea is that since the TCB is small, we can kind of manually examine it and run it and test it and all that. Although there's no like a very solid way of building the trust on the TCB as well. But then everything else, we have a mechanism to kind of bootstrap the trust. So it's kind of like, again, cryptographic mechanisms or system level mechanisms for trusting that. So usually it's just to start with what we call secure boot. The system basically first boots into this TCB, and everything else is boots from the TCB. And since we trust the TCB and we trust the kind of the transition from the TCB to next one, we kind of then start trusting these chain of activities. This is how we basically build our system. So these are the main three principles of how we build our secure systems. So now the fundamental question is that, does this work? And of course, the answer is no. If it did work, then we wouldn't be here, right? So why it doesn't work? You already seen an example of this in the last lecture through cache side channels. Essentially, the main thing that digital side channel does is it breaks this isolation assumptions between the processes. So, for example, in the cache side channels, what you have seen is one process can actually access some sort of, not directly, kind of indirectly, the patterns of the other process, and the result infer something, right? That's is equivalent of like assuming that I'm kind of be able to read the other process data, which, as I said before, the assumption was we shouldn't allow this to happen because of the isolation. So we're not directly reading it, we are reading it through some kind of like a weird way of like reading the patterns, as you've seen in the previous lecture. I'm going to quickly also overview it in the next few slides, but that's the main reason that this happens. And as I said, cache is only one example. There are a bunch of others that all of them, what they do is just breaking this isolation assumption, basically. Okay. Why this exists? It exists mainly because of contentions. So the way it works is that this side channel thing creates some form of a contention that can be measured. And this measurement could be, as I said, directly or through some form of a timing behavior. Unfortunately, this contention is there because we want to make our systems more efficient and more power efficient. So do you want to share things? So that's kind of a principle that whenever you design things, the main thing that you would think about is that, okay, let's share things to reduce the power or reduce the cost. But that the same sharing is going to basically cost you with security. So how side channel works? You've seen in the Monday's lecture that there are a bunch of different ones. The one that I'm going to talk about is the prime and probe one. I'm going to just quickly go over it one more time, so for everyone to review, and then we're going to move on to the defenses. So let's say I have a shared cache. It could be L3, it could be L2, it could be L1. These are our sets. These are our ways. In this case, we have a 4-way set associative cache. Have just say 2 processes, the victim process there and the attacker's process here. Of course, as I said, if the attacker, if the victim, for example, puts some data here and the attacker tries to read it directly, this will not be allowed because of the isolation. So essentially, whenever we do this, the operating system checks the addresses and see that this address belongs to that process, but this process cannot read it directly. What we do instead is this idea of a prime and probe. The essential idea is that, okay, let's not read the value, but read the value in a way that it's actually impacts something else. So for example, let's say that, if some secret value P is a binary value, P could be equal to 0 or 1. But then if this P impacts the victim's process to somehow access the cache or don't access the cache. So for example, let's say if P is equal to 1, it accesses the cache. If P is equal to 0, it doesn't access the cache. I'm going to show you an example. You've probably seen an example in the Mondays class as well. But let's say, for example, I'm reducing the problem to just P equal to 1. I'm going to access the cache. P equal to 0. I'm not going to access the cache. Okay. So in that case, essentially, if the attackers can see whether or not I access the cache, they will know the value of P, right? So if after this process, this attack process, the attacker infer that no access has happened by the victim, then the answer of the P is 0. If the attacker sees that, oh, there was an access, I don't see the content of the address, I just see that there is an access, then it means that P was 1. That's how the attacker inferred this secret value. How does it work? Essentially, the way it works is, as I said, it doesn't work directly because of the isolation. So the attacker says that, okay, I'm going to have these 3 steps of priming, weighting, and probing. That first, I'm going to create what we call an eviction set. And the eviction set means that the adversary tries to find sequence of addresses that all map to the same set. A lot of works that actually been trying to create this eviction sets nicely and fast enough. So there's kind of a lot of theoretical work even in finding these eviction sets. But essentially, eviction sets could be as simple as I just try many different addresses until I find 4 addresses that maps to the same set. Okay. So let's say that, for example, that process is done. Then the attacker is going to access them one by one, 1, 2, 3, 4. These are 4 different addresses. The result of this is that the set's going to be filled with adversary's data. What is inside each memory cell doesn't matter. It could be any arbitrary values. The fact is it belongs to the adversary. That's the only thing that matters here. Then the adversary will wait. And as I said, P equal to 0 means that the victim is not going to access the cache. P equal to 1 means that the victim is going to access the cache. So 2 things might happen. Either the victim is going to access or not access the cache. But since this access is on the same set as the adversary prime, then the result of that access is that one of these, doesn't matter which one of them will be kicked out. Okay. Because cache always kind of like, tries to remember the most recent things. That's the whole premise of the cache, as we're going to talk about later about the performance of the cache. So generally, whatever is newer, we try to memorize that. That's the whole point. So as a result, if the victim accesses the cache, you're going to evict one of these guys. And then that's when the attackers say that, okay, let's see whether all 4 of my contents were there, or at least one of them is out. It could be multiple out, but at least we know for a fact that if none of them are out, that P didn't touch this cache set. As a result, victim didn't touch this cache set. As a result, P was 0. If I see at least one miss, then I'll know for a fact that this victim accessed this set. Right? So basically, we're going to measure we're going to read these 4 addresses one more time, and we're going to time it, right? So how do we time it? There are actually instructions, unfortunately, and very conveniently for the attackers, that there are instructions that you can time things very easily. There are also other kind of like more clever ways of timing things. So for example, you can, let's say, like run a for loop and see how long does it take to finish that for loop. And that would be kind of an indirect way of timing things. But most of the modern processors, including all of the Intel processors, has literally an instruction called RDTS TC or TSC, which is basically just read the timer clock. And you can start it, and then you can read this, and then you can stop it. And then if this value is small, it means that it was in the cache, because generally the premise of cache, again, is that if it's in the cache, the access time is short. If it's not in the cache, the access time is long. So I'm gonna see that basically if I see short, it means that all four of my data is there. So P was in fact equal to 0. Otherwise, if I see at least one of them is long, then I know that P is equal to 1. Okay. So that's kind of the premise of prime and probe. Unfortunately, this is actually possible in many very critical applications, including some of the crypto algorithms. This is again something that was discussed on Monday. So the critical part is this part, that based on the secret value E, which is actually part of the RSA key, if E is equal to 1, we're going to have an axis. Otherwise, we're going to basically skip over this. So this creates the timing channels that Philip mentioned. And essentially, if E is not equal to 1, we're not going to have this. And as you can see, this is actually will translate into a cache axis. Okay. So basically, the attacker will see that whether this access happens or not. If it didn't happen, that bit of 0, E itself is a vector. That bit of 0 was 1. So essentially, the attacker can go through every single bit of the secret and build this and have the results. This is kind of like another example of this algorithm. As you can see, that you see either a behavior like this or a behavior like this. That's kind of like the 2 steps. So that means that there was the second part and the first part. This part you see that it's much shorter because the second part is kind of skipped. So you only see the the multiplication, the modulation, but not the multiplication. So the attacker basically kind of like can see this. So this, for example, is like 1 and then another like 0 and then a 1 and then 0 and then a 1. And this seems to be a 1 and then a 1 and so on and so forth. So essentially the attacker can like window this and extract the bits very, very accurately with this very easily. So this is basically the sequence that can be deduced from the system. Any questions so far? Yeah.
So earlier we had those 3 principles. Why do we need principles 1 and 2? Like, are they like the same thing? You can only access your own resources and data, and then you can't access other people's. That same thing.
Well, so the principle of least privilege means that you need to, but think about this, is that your own thing is, how do you define it? Like, is your own thing everything, or is your own thing some of the things? How do you define that? That's why we call it least privilege. It means that we have to give you the minimum possible.
Okay.
That you can still operate. So, for example, if you need to access, I don't know, particular IO, if you really, really need to access it, then there is a process to give you that access. Otherwise, by default, you don't have access to the IO.
Got it.
Yeah. There's also other interesting attacks. For example, more recently, people have shown that for cache, you can also use the pattern in the architecture of a machine learning model. Because essentially, if you think about like a kernel, a matrix multiplication, it's very structured. And you can actually see, for example, the size of the vectors, the size of the multiplications, and all that based on basically the cache patterns. And then why would be this useful? Because then you can basically store the IP. So for example, let's say, I don't know what exact model you're running on this system, but I can measure the cache patterns, and then I can say that this is the exact architecture. This is like, the number of layers, this is the size of each layer, and so on and so forth. So especially now that all these kind of like models getting more and more complex, this is an important information that companies can basically steal from each other. And then again, in the lecture, you've seen that there are very different variants of this depending on the assumptions. So the ones that I showed you, and the most prominent one is prime and probe, because prime and probe doesn't have any sort of assumptions about the system. But there's a whole bunch of other ones like flush and reload and flush and flush. And there's another one called takeaway, and there's another one called a streamline, and so on and so forth. I think some of them will be covered in the paper presentations. But if you're generally interested, follow this pattern. This is another example. This is the flush and reload. And again, covered on Monday, that the difference between flush and reload and prime and probe is that we assume that there's some form of a sharing going on between the victim and the attacker, although not that particular data, but some form of a page that's being shared. Why do you want to share pages? Because in many cases, you need to share pages for things to operate. So, for example, you have a thread system and you want to be able to share it. The attacker basically measure, again, same principle. You load things, you check whether or not that has been kicked out or not. If not, P equal 1. If yes, then P is equal to 0 or other way around. Essentially, you reduce it to some form of a binary decision and you make that decision. Okay? And then again, is the cache is only way? No, anything that is shared, kind of the same thing. So essentially, you create some form of a timing, you make some reduction to some binary decisions, access, no access. That's the meaning of things, and then you kind of back propagate this into the algorithm that's being run on the system, and that way you can actually extract the secrets. All right, so. And then, by the way, these are some of the examples. So, for example, TLB has been attacked, DRAM has been attacked, GPUs has been attacked, branch predictors has been attacked, and these are actually these are mostly, as you can see, these are like 2018, 2019, so on and so forth. There's actually a whole bunch of new papers after 2020, including some that you're going to see in the paper presentation. So the one idea in the paper presentation is that you're going to see the more of like the latest and greatest attacks in this domain. Most of them by basically follow the same principle. Really, the kind of states of the research for this particular topic is more of like people really get into very, very details of the implementation of this modern processors. And they figure things out and they kind of like show that how you can basically apply to another microarchitecture units in the system. That's really what's going on at the moment for most of these attacks. All right, so how do we defend this? And that's the goal of this lecture mostly. Any questions so far? Okay, so give me answers. How do we defend against cache? I kind of gave you some of them, but let's actually formalize it. Let's discuss it. Yeah.
Just have separate caches and
You can separate caches. That's always the best option, right? So you just isolate them. What are the trade-offs though? What do you lose by separating caches?
the performance.
Some
You just
performance.
have better two cores sharing cache,
Mhm.
perhaps they're sharing something, or even if they're not, maybe one core needs more cache than the other.
Yeah. And then if you want to separate them, how do you separate them? Do you separate them all layers? Do you separate them as some
They're
layers?
using all layers to be separate.
Okay. And then do you separate them as like all the ways or all the sets or everything? What do you do?
I mean, I guess you could separate the ways, that would be, that's probably the best,
Why would be the best?
because then you still, well. Actually, it's basically just two separate caches then, right?
Okay.
It's the same thing, two separate caches, separate the ways.
Would it be better to separate ways and not having the same structure in separate ways or having like completely two separate caches?
I mean.
Anyone else and also can chime in.
I think it wouldn't, it shouldn't really, if it's separate ways, I like you can't really affect the other processor's
Mhm.
cache that much, or at all, I can't think of any way. I
Okay.
think that would be enough.
Okay. What about sets? Can I just partition sets and not ways?
I think so, I mean, I think either one works, as long as the condition.
Which one do you think is better?
Probably sets,
Why?
maybe it doesn't even matter, but. Because then you still, because if you have less ways, you're more likely to get conflict misses.
Okay. Yeah, good thinking. These are all like the ways that you have to think about this. So essentially you go down the roads and ultimately you want to minimize the performance. And we're gonna actually go through this cache partitioning. Any other ideas or suggestions?
At least my understanding is that the way that this hack works is based on if you have like a data dependent computation based on your metadata. So my idea is like, what if you just write your program such that you don't have like this data dependent? Like for example, here we did a memory access. If you have 1 and not, we'll get 0. But what if like if you see 0, you do some like nonsense memory access?
Okay. And what would be the trade-off for that?
Obviously, then your program is slower.
Much slower. Okay. And then how do you gonna detect that kind of like if then else's? Are you gonna, is it the burden on the programmer to kind of like, oh, if you write an if, you have to write an else?
I mean, the easiest way to implement this, yeah, put it on the programmer, but I guess maybe the compiler could like insert these kind of memory accesses.
Okay. And do you think we need to do it for every single if then else's in our program?
You could probably identify like critical ones.
Okay, cool. Any other suggestions? You have?
Yeah, you could make certain like commands super users such as flush or,
Uh-huh,
cause I know they've done that in the past.
uh-huh. So you don't allow things to be flushed unless you really have to.
Yeah.
Mhm. But then what would the trade-off for that? What do you lose by that?
Oh, because flush happens when you have like inconsistent between cache and like the main memory, right?
Mhm.
You flush it to basically
Mhm.
make it okay.
But no, so let's say, okay, I make it only privileged, which means that now at the user level, I no longer have that capability. What would be the trade-off for that? What would be the downside from that?
You could have some messed up data or messed up calculation.
Alright, so it's convenience and then even some performance in some cases. Mhm. You had something to add?
Yeah, so I think one of our biggest things is we're kind of using time to get all the information out of this.
Uh-huh,
So if you could somehow obscure the timing,
Uh-huh.
for example, like if we could just make it constant.
uh-huh,
Obviously, the trade-off would be we have a bunch of latency, or maybe instead of that, we can add some noise to it to make it a little less predictable.
uh-huh. Okay, so make the timing more difficult.
Yeah, so that
Okay.
the information is obscured.
Okay, okay. Any other suggestions? These are all very good suggestions. There's one more that I'm looking at. Anyone?
Could we do some sort of detection of the actual like adversary?
We can also detect, yes. Detection is more of an after the fact, but yeah, we can also detect. That's a good answer. Any final thoughts? Okay, so these are all good answers. Actually, these are all almost everything. I think there's one more bullet points that you guys missed, and we're gonna talk about that. But yeah, so let's actually talk about them. The first one is as said that you can actually make everything constant. That's a very common solution. This is called constant time programming or oblivious programming. Constant time programming is actually a very old idea. Because before cache side channels, there was power side channels and EM side channels. And they also work in the same principle for this if then else's, because essentially, for example, just substitute cache patterns with power consumption pattern. If the if then else's, for example, if your if condition takes more power or less power than your else path, then the adversary who measures the power can actually kind of infer whether you've taken the if path or the else path. So very much before cache side channel became a thing, because cache attacks kind of became mainstream in 2010s kind of decade. So it's like the prominent papers came out in like 2014, 15, and so on. Power side channels were introduced in early 2000, even 1999 and so on. So that's why about the 10 years, there was actually a lot of works on constant time programming. And how do you actually write constant time programming? How do you write constant time programming? So there are two options. Either the software developer understand this and write it, or the compiler, as we mentioned, can actually go through the paths and try to kind of add things to different paths. And of course, the key thing and key kind of innovation is how do we make this overhead small? And then again, another idea that came out is maybe you don't need to constant time everything, maybe just a particular function that you need to constant time. But then the question is, how do you decide what that function is? How do you keep track of that function? So there is all sort of challenge with constant time program. Another thing that is also being done, and it's also very interesting, is something called an ISA extension. So you can actually use commands, instruction commands that can do some of these things. So ISA could also help you. So you actually, when it's translated into instructions, for example, you can have, let's say, a constant time load instead of a regular load, right? And then you can substitute a regular load with a constant time load, and that gives you kind of a behavior that you want. So essentially, to give you a little bit more detail, generally there is this idea of we have a real path and a decoy path. And then essentially, regardless of the input, each input should take both the real path and the decoy path. So you essentially need to run both your if condition and else condition. Typically, the way it's that we kind of can have some form of what we call a predicate-based execution. Or you can have some form of specific instructions to run both. In order to kind of track what do we want to kind of protect, there is this notion of what we call taint tracking. How many of you have heard the term taint tracking before? Okay, no one. So the idea of taint tracking is at the software level, think about it that this way, so that I have, let's say I have int secret, and secret is, let's say, equal to some initial value. But then I have, let's say, another input, like, another variable that is like secret plus, I don't know, like another variable b, okay? So let's say my secret is indeed the value that I'm worried about, okay? So I'm going to taint my secret. So I'm going to watch it. But then secret, unfortunately, is not like an isolated thing. It interacts with the rest of the program. Otherwise, there's no point of using it, right? So for example, in the very next instruction, you will see that secret plus some non-tainted value, non-important value is being updated and written into another value. And since the source is tainted, source is secret, the destination or the sink is also should be tainted, because essentially the value of A is indirectly relevant to the value of secret. And then you kind of continue this kind of taint tracking. That's why we call it taint tracking. That essentially what it does is that you track this taint, and you taint more things, and you kind of like move forward with this. You add more and more things. There's at some point might be very complicated things, but any sort of memory writes that involves a secret, any address that involves a secret, any variable that involves a secret, you have to keep track of it. And then, for example, later on, if I have A plus some C to some D, then again, D has to be tainted and so on and so forth. And of course, at some point, you have to untaint things as well. Basically because, for example, this has been like zeroed out or removed and so on and so forth. How do we do this? You can actually write programs and do it at the software level. There's also a lot of interest in doing taint tracking in hardware level. And there's also, again, lots of works in this domain for doing sort of taint track. What the trade-off here is that you need to do a lot of, so one idea is that, okay, I treat everything as secret. So in that case, I don't need to taint everything. Everything is already tainted. That's kind of get rid of this premise. But unfortunately, that means that everything will be slowed down significantly. So as long as my secret and the taints are a small fraction of the whole program, it's beneficial to do it this way, okay? Otherwise, if this is gonna eventually taint 80% of my program, then there is no point. I can just get rid of it and just treat everything as secret and move on, okay? So just keep that in mind, that there is this kind of tricks that one needs to think about. But another question, yeah.
And so does that happen like before the program statically or dynamically? If it happens dynamically or statically, how does it, or both, how does it handle like branches?
So it can happen both dynamically and statically. As I said, if it happens in software and using compiler, then it's more of a static thing. If it happens in hardware, it's more of a dynamic thing. So essentially, you need to augment your pipeline, for example, that every write to the register is also check this kind of 1-bit flag of whether this is tainted or not, and then you kind of propagate this. So with the value, think about this, that every value is now 1 more bit that is kind of say 0 or 1, and then there is conditions. For example, if you see a 1 in the source, then the destination also will inherit that 1. So if there is at least one of the two sources that is tainted, then the destination should be tainted and so on. How do we handle branches? The same way that we handle. And again, so you can, for example, say, if it's kind of like assignments like this, then it doesn't matter whether it's inside the branch or outside the branch. But if the branch itself, for example, is based on the tainted value, so then that's where you're going to do this kind of decoy path and real path. If the value, for example, is not based on the secret, then you don't care, right? Because what if the attacker knows that whether you take this branch or not, there is no secret about it, so let's actually move on. So that's the whole, actually, again, that's where you're gonna save in with this. Any other questions? All right, so another question about this is that, okay, let's say I actually make everything constant time programming. Is that enough? Are we good? Anyone? Think about cache, for example. If I make everything constant time, and you think about an attack that breaks this.
If you try to monitor different areas of the cache,
Mm-hmm.
maybe, I don't know, temperature, heat,
Mm-hmm.
emission, electromagnetic.
Mm-hmm.
The heat, you would probably get away with monitor if you can get access to the heat sensors,
Mm-hmm.
and then monitor how different areas, how the heat, different sensors, temperature values change based on different areas of the cache.
Uh-huh. Okay. And then you're saying that essentially if they both access the cache, but different areas of the cache, then you can say that, okay, this one accesses this area, the other one.
Yeah.
Yeah. Yeah, you can even, like, you're actually making it even more complicated. Think about, like, I just can see the addresses, right? So I can somehow monitor the addresses. If I can tell that, for example, this particular input access this part of the cache, but the other one access the other part of the cache, I'm gonna leak information. Both of them have the exact same time because both of them are accessing the cache, but just different locations of the cache. So again, the important thing is that the timing is very important, and that's the main thing that you want to protect. But the microarchitectural footprint is also something that's important. So the next level type of attacks these days that people are looking at is not only just fixing the timing, but making sure that the footprints is also exactly the same. So if this one is accessing this set, the other one has to also access that set. If it's accessing a different set, then potentially the attacker can differentiate between these. Or, for example, like, the ultimate version is, oh, I measure the temperature, or somehow can differentiate between these different aspects of the cache. Okay. All right, so that's number one. So the first option is fixing it as kind of the source. That's a very good thing to do, because that's kind of decouple it from how do you do things in hardware. And that's what many people do, and very popular solution. But then we can actually do things in the hardware as well. The very common one is partitioning, and that's what's kind of like the long discussion that I have with Jacob of different types of partitioning or isolation. So you can actually partition in different ways. So you can partition the sets. This is actually a paper called Chunked Cache, which was published a few years ago. So the idea is that, for example, you have what they call isolated domain or even non-isolated domain. So for non-isolated domain, you can just give a big chunk, say, okay, set number 0 to set number 8, all shared among all the processes of this non-isolated domain. But then if I have domains that are isolated, I need to really protect them, then I'm gonna have it like separate domains for each one. So I'm gonna partition the cache into multiple instances or multiple kind of domains, and then assign few sets to each one of them. And then kind of like, then I need to kind of like keep track of, oh, what is the global set and what is the chunk set. There are some implementation involved that I don't want to bother you with that, but general idea is that then these guys is kind of like a regular cache, so they can fight with each other and do whatever they want with it. But I don't care because there's no secret values involved. But the ones that I'm really worried about, I'm going to give them some form of isolated. And as you can see, usually, of course, the one that is non-isolated should be much bigger than the isolated ones. But then what would be the downside of this, as we can discuss, that you can see that immediately what used to be, 16 sets with multiple ways, now this is like an 8 set. So we kind of cut the cache in half for non-isolated. And since most of the people care about their regular applications, they don't care much about their secure applications. Basically, what you're giving this to them is that you're dividing the cache by half, so the performance is going to be much, much worse than what used to be before. So that's a big issue. Got a question?
Is there like a way to have like dynamic partitioning?
that's a very slippery slope because essentially at the moment you introduce some form of a dynamic behavior, the adversary can see that, right? So if you don't make this rigid and you're kind of saying that, okay, so sometimes you're going to give this and sometimes don't, then the activity here going to be revealed. So the adversary that sits in this part, if it sees that now all of a sudden they have more space, they're going to infer some information. So you're going to leak some information. Whether or not it's possible to do that, there are a few papers of kind of looking at this and trying to decide what's the best way. Maybe you don't do it dynamically in that fashion, but there are papers that shows that, oh, maybe I can sometimes, if I don't see any of these guys, I give everything to the non-isolated, and then if it really needs to, then we grab it. Another thing is I can have different views of the cache. So from the non-isolated wards, this thing is rigidly partitioned. So if it tries to, for example, access here, I'm going to block it. But from these isolated domain, they see everything. Kind of, they can put everything wherever. So, and then kind of like in the background, they kind of handle where to put where and so on and so forth. So instead of like saying that, oh, these sets are for you, this sets are for you, there's some form of a translation going on in the background to kind of make this. So there are like lots of interesting ideas. Again, this is an active area of research, lots of papers in this domain trying to do this. A good thing about this is for performance reasons, there is actually interest in partitioning the cache on the fly. So there is this thing called CAX. There is cache access level technology or something like that. I forgot what's the stand for CAT. But essentially the idea is that Intel processors has this capability where if you have a bunch of applications, for now, don't think that these are secret, so there is no security involved here. Let's say I have 3 different applications, okay, that try to use the cache together. In order to ensure that there is a fairness between these applications, you don't want one application to hog all the cache, okay? Because if one of these applications is essentially like fill their data, entire cache with their data, then the other 2 applications are going to suffer. Basically, they're going to experience a lot of misses, okay? So in order to make sure that there is some form of a fairness such that everybody kind of have some level of access to the cache, many of the modern processors try to limit the amount of access of each of these processors to the cache. Not for security reasons, again, just for the fairness reasons. Another thing that, again, this is going to be a topic of discussions of one of the lectures, is that there are some applications that are not cache friendly, which means that they just access things one after another without really reusing them. Think about video streaming, right? So video streaming is an example of something that you just read things off of memory without ever going back to them. But unfortunately, it puts a lot of strains on the memory and bring a lot of junk data to the cache, right? So think about like you're streaming like a video, movie, you're essentially constantly just creating accesses load to the memory, and that brings a lot of data to the cache without any reusing, because you never go back and see the same frame. You just move forward, which is a new data. So that if I don't put any sort of guard blades, then essentially if you're someone who is watching a Netflix on a web server, essentially just basically what we call thrashing the entire set. So whoever else that's using the same server is going to experience a very terrible cache performance because just someone is watching videos, okay? So servers, clouds are actually very smart on this. And then if they see that, oh, you're just streaming and you're not using any sort of patterns, they're going to immediately shrink your size of the cache because you're not going to use the cache anyway. If I give you 0 sets versus all the sets, the performance is exactly the same. At least the other guys can use it. So this is this advanced technology. But now the idea here is that now we want to somehow do it for security, and for security you have to be careful because, as I said, I told Jerry, if I do this dynamically, then the adversary will also understand this. So you have to be very tricky. There's actually an interesting paper called DOG, which is which is kind of an answer to the Katz paper that was kind of trying to do this this dynamic way partitioning. So this is dynamic way partitioning. This one is cache access technology or something like that. You can, as I said, you can also do it at way. So for example, this is RISC-V technology. It's actually what's called this is the trusted execution environment based on the Boom core that we are talking in this class. So in the normal, system, let's say you have a bunch of like different applications. You have the untrusted one. This is a secure machine, which is kind of think about it as like a secure app, and then a whole bunch of other enclaves, which is again some form of a secure apps. In regular system, last level cache, essentially free for all kind of thing. Everybody can sit everywhere. And then in the DRAM, you're gonna have the isolation. So this is a standard system. Unfortunately, this is vulnerable to cache side channel attacks, obviously. So the way that we can do this is that we can do cache partitioning, but not in the sets, but in the way. So for example, say way number 0 and 1 is for this application, for enclave applications, which are secure applications, and everybody else has to use the others. I can then even go further than that and then kind of like divide the ways even further and assign ways to particular things. I can also go further than that and encrypt things as I talk to the DRAM. So encrypt the patterns and encrypt the data. This encryption could be software implemented or it could be hardware implemented. So the reason that you want to encrypt is that I don't want the adversary to even see which addresses I'm accessing to the memory or which content I'm sending to the memory. Later on, I'm going to revisit that when we're introducing the notion of oblivious RAM, which is not only the cache is oblivious, also the memory patterns is also oblivious. But all of these means cost, right? So this means that the size of the cache is shrink. This means that now every access needs to be encrypted, decrypted, and so on and so forth. So there's a whole bunch of engineering that needs to be going on here to fix this issue. Okay. And then again, trade-offs, way versus set. So you kind of like saw the different things. You can do it static or dynamic. You can see cache friendly versus cache unfriendly, and so on and so forth. All right, so let's have a quick break. Then we're going to talk about the third option, which is randomizing the cache. This is the one that you guys didn't talk about. So I'm going to give you a little bit more detail today. Continue. All right. So the third option is make it harder for the attacker to observe things. Okay. And mainly the main thing that most attacks do, so most defense does, is making hard for the adversary to set up the attack. What do I mean by that? If you think about the attack, especially like a prime and probe type, the very first step is that the adversary needs to kind of figure out a set of addresses that maps into the same set. If you make this very, very hard for the adversary, then the adversary cannot even set up the attack, and it doesn't matter whether or not the adversary kind of accessing anything in the cache. It's not easy to measure. The other option here is making the timer more noisy, as you mentioned. That's actually one of the solutions many people looked at. Unfortunately, the timer one is much more tricky because there are other ways of measuring time. So there's like what they call timerless attacks. There's like ways that you can use like your own instructions as a timer. So there's a whole bunch of these attacks that doesn't use any sort of direct instructions as a timer, but that's definitely one of the viable solutions. So let me actually talk about this paper called Caesar, which is an interesting paper. So the idea of Caesar is cache address randomization. So you can think about like a regular cache as the virtual address comes, you make it somehow to a physical address, and then you directly access your last level cache. So what we can do instead is we are adding this decryption, encryption, or this mapping in general blocks. So in terms of like, if you want to call it encryption, we can basically take the address and create this new address. So physical address and encryption address. And then what it does is basically it just takes an address and map it to another address. Okay, so that's all it does. It's a one-to-one mapping, and it has to be one-to-one mapping. And of course, it has to be reversible so that you can also read things off of the cache. But if I do that, then essentially the adversary that creates this physical address does not see the actual address there. To some extent, this helps at least for transferability from one system to another system, so that if the attacker kind of figures out how to map 4 different addresses into an LLC of this cache, then if it tries to run it in another system, since this encryption is this mapping is unique to each device, then at least the attacker needs to rerun their kind of setup phase to find another 4 addresses that maps into the same set. And then you can also do this for after each reset on the same computer. So essentially I can set up, I can reset this mapping every time that I reset my system. So again, it means that after every reset, the attacker needs to run this again and again to find that addresses, okay? So that's kind of a good start. So essentially what this does is making it harder for the adversary to fix it, but this doesn't, completely fix the problem, because the adversary can always run. So essentially you just make it the level of indirection, right? So it's not like you're not making it impossible, you just make it more time consuming for the attacker. So essentially the adversary basically runs again this dynamic search and find it and find the address. How soon they can find the address? Essentially, what they need to do is that think about that if your last level cache is only 4 sets and each set has 2 ways, essentially the adversary needs to find 3 addresses that maps into the same set, because the moment that they found this is basically 2 of them are the addresses that the adversary can use. Okay, so how soon can we find this addresses? This depends on the size of the cache. In fact, for like a large cache, this is within tenths of a second. So 10-20 seconds, I can actually find multiple addresses in the same set. So this doesn't completely fix it, but there's actually a solution that we're going to talk about to fix it. But before that, I'm going to actually use this time to talk a little bit about probability. It has nothing to do with computer architecture, but it's this kind of bucket and balls is actually this problem is actually quite interesting problem. I'm always fascinated by this. So let's actually take a detour of architecture. Let's talk about probability. So the question I'm asking you is, if I have a problem like this, how many balls? So let's actually create an analogy. Let's say each set is a bucket or a bin, and each axis or each memory is a ball. Okay, how many balls do I need to throw to this bins until I make sure that I have at least 3 balls into the same bucket? Anyone wants to answer this question? This is a classic problem called bucket and balls problem. It actually has lots of use cases for load balancing. So networking is actually used a lot. Who thinks that they know probability very well? Who's confident about their probability skills? No one? Semi confident. So first of all, how many balls do I need to throw to make absolutely sure that there is at least 3 balls in one bucket? Yep.
The entire cache size plus 1.
The entire cache size plus, I need 3 balls.
It's 12.
2 times, right? So 2 times the number plus 1, then I make sure. But what is on the average, do you think? Like intuition, what do you think should be the number?
6. 6.
6? Why 6?
I don't know.
All
You said intuition, bro.
Alright, so let's actually talk about another problem. How many of you have heard this birthday paradox problem? Okay, so that's good. So the birthday, for those of you who don't know what is the birthday paradox, the birthday paradox basically asks this fundamental question that in a classroom like this of n people, let's say, I don't know, we have like around 30-ish, 40. What is the probability of at least two people shared? Like, how many people do I need to have? Let's ask it this way. How many people do you think we need in this class to have at least more than 50% chance that two of them share the exact same birthday? So those of you who know the answer, don't say it. For those of you who don't know the answer, what do you think the number is? So I want to have at least enough number of people that I can say at least there is a 50% chance that they share the same birthday, at least two of them. Not all of them, of course. Anyone wants to just guess a random, just give me just a random number. Doesn't need to be correct. Yeah.
Have like 184 people, then you can cover half the day. So then if you add another one, then the likelihood that they're that half is like at least 50%. So like 180.
180. Okay.
Yeah.
Anyone else wants to bigger? First of all, what's the number that you know absolutely sure that we have at least two people? 366 is the ones that, but we want to know at least two people, and on average, of course, it may or may not happen, but I want to have at least 50% chance of having two people. Anyone else wants to throw a number? Those of you who don't know, how many of you know the answer? All right. Those of you who don't know the answer, give me another prediction. Maybe something less than 180. And this is a paradox, by the way, so the number is a little bit surprising. You know the answer?
No, I'm trying to think.
I'm gonna make a wild guess, it's somewhere in the 30s, like 35.
Okay. Do you have any reasons for it?
Nope.
You just
I
feel
think I'm
like
trying to come up with a reason. I can't even come up with a reason.
you just feel like 30 is a good answer.
Maybe 30s because that's about as big of a month.
Okay. Yeah, could be. All right. So those of you who know the answer, what is the answer?
It's like
Aiden.
around 30, actually, I think.
Yeah, it's 23, I think. So 23 is the number that if you have 23 people in a room, there is at least 50% chance that two of them share the same birthday. Yeah.
So in this room right now?
Test it.
Probably we can test it. Yeah. I don't know. Like, how many of you have been born in January? Okay, so like 1 to 15. Okay, so what is your birthday?
7.
4.
Okay, so we missed on that one. Oh yeah. Wow. All right, cool. So second half of January. It's only one. Okay, so January is gone. First half of February. Only 1%. Second half of February. Only 1%. Okay. First half of March. All right.
Just
So
a
what's
lot of-
13.
13? 7?
8.
Second half of March. Okay, so we have few, yeah.
27.
27.
21.
Ah,
25.
25. Oh, yeah, there you go.
The heck?
So we hit it on March, so that's good. And do we have anyone in November?
Yeah,
You?
it's 27.
Okay, on the 6th of November, if that helps, but. All right, so it works, but it's a probability, so it may not, it's not like guaranteed, of course. So how does actually this works? You can actually plug in the numbers. So for example, you can say, okay, for the first person, of course, 365 out of 365. The probability of the second person not being the same person is 364 divided by 365. Third person should not be any of these two guys, so 363, and so on and so forth. The probability of like this doesn't happen is that these numbers should be all multiplied together, and the actual probability of no shared birthday, if you actually do it all the way to the 23rd person, which kind of comes out at 343, divided by 365 is around 50%. So the probability of shared is 1 minus that, so that's where you're gonna get the 50. There's actually some form of a closed, like approximate closed formula for it, is the square root of 2 times n, the natural logarithm of 1 over 1 minus p. In this case, for example, I asked you what is the 50% chance, and n is the number of days. If you plug in the numbers that you're gonna get, n is around 22.48, which is, that's why we kind of come up with 23 here. So that's the birthday paradox. It's a very interesting probability questions that some of you might see it in your interview questions. So now you know. And it's kind of surprising. That's why it's a paradox, because essentially it's like the number is significantly lower than what we think, right? So it's 365 days. You think that 23 people is a very small number, but now you know why it's like that. There is another interesting problem that's called coupon collector problem. How many of you have heard this one? No one? Oh, 180 doesn't cover.
Promo codes these days.
180 doesn't cover coupon collector. Oh, okay. So this one is more interesting then. Again, these are not directly relevant. You're going to see how it's relevant to the cash problem, but I'm just generally interested by probability is one of my favorite topics. So when there's the opportunity, I'm going to use this. So the coupon collector problem is, let's say there are n different coupons. In this case, let's say there are 5 different coupons. And then you want to buy a bag of chips, and each bag of chips has 1 coupon, has always 1 coupon. It's a randomly generated, right? So if you buy a bag of chips, it comes with a random coupon. And every coupon is equally likely. So there is no like a particular distribution for one coupon versus the other coupon, although there's a specific part of the question of, like, you know, smaller sub-problems of this is that if this is not uniformly distributed. So now the question is, if you want to collect all 5, let's say you're going to get an A if you collect all 5, how many bag of chips should you buy to get all 5 with some good probability? With on average gets, so on average, how many bags do you need to get to buy to get all 5? Anyone wants to get a wild guess for this one? So in this case, so then of course this is for, could be for n. Let's say for now, we're talking about just 5 coupons. How many bag of chips do you think how many minimum bag of chips you can buy to get all the 5? 5, of course. But then how many what's the max? What's the ceiling? Like how many bag of chips I can buy and say for sure that I'm gonna have 5? Infinite. So if you're like in the unluckiest sport, it's not infinite. Basically, it depends on how many bags of chips have been, made, and then since it's uniform, it's divided by 5 minus that is the number. So it could be like a lot, right? So now the question on the average, how many should we buy? What do you think the number is? Again, give me just your wild guesses. It doesn't have to be correct. Yeah.
8.
8. Okay. You feel very lucky.
Really?
Why 8?
Well, I was just thinking, so each has the probability of about 20% to appear. So, if I expand that with the through 2 chances, so there's like, this is probably the wrong math entirely, but I'm like, so like 60% extra chance right there.
Okay. So you say, okay, if you miss on like 3 of them, it's still 50% over.
Yeah.
Okay. Anyone else wants to throw in another number? Yeah.
25,
25, okay, why?
because you're 5 coupons.
Okay, oh, so you buy 5 of them and say, okay, there is 1 in each, okay. Yeah, that's also a good answer. Yeah. What? 12, okay. Why?
I did math that I'm pretty sure is incorrect, but I'm gonna throw my number out anyway.
12 is actually the correct answer. Can you tell us the math?
I think I did the math.
All right, so let's see why 12. Actually, either 12 or 13. I think it's like 12 point something.
11 and a half.
Yeah, I think it's 12 point something. But So first of all, the answer, of course, is random. There's no like one final answer. It's not like a paradox problem. If you're lucky, if you just purchase n out of n, then you will hit it. You cannot obviously buy less than n and have all the n's. If you're unlucky, then you have unlimited number of. If there's unlimited number of bag of chips, then you have unlimited, and you're still not gonna win it. The more suitable question is, okay, how many purchases one needed on average to collect all the coupons? And then for n equal to 5, we said that it's around 12. Actually, one like a simple intuition is, actually, let me answer the question more concretely and then go with the intuition. In order to understand that, we need to go through the random variables. Geometric random variables, how many of you have heard the term geometric random variables? Okay, good. So at least we're teaching you something in undergrad. So if you have a sequence of independent trials, and then each trial is just a success and failure. So you just like think about like, you know, a flipping coin. Then if the probability of success on every trial is P, then if you have a geometric random variable X is essentially defined as the total number of trials needed for the first success. So for example, flipping a coin, what is the probability of success of having a head after like X many trials? Yeah. 50%.
To get ahead.
After the certain amount of tries, yeah.
Yes, but I mean, if you, so the chance of success, so basically what I'm saying is that if you do it n times, even if you get it one time, I call it a success, not like in the end time. Yeah?
Wait, is it just 1 out of any time or is it at the end? If it's at the end, then it's 1 minus P.
You said anytime.
The end minus.
Anytime. So either like if I do it n times, 1 out of this n, if I get it, that's what we call success.
Then so P to the 1 minus P to the n minus 1 times.
Yes, exactly. So that you put that actually, if you actually do it for infinite, it's going to be 1 over P. So essentially, if every trial is P, then this probability of this expectation value is 1 over P. For example, for flipping a coin, you would expect that after 2 times you get at least 1. So that's kind of the expectation, right? The intuition is that, like if something happens 1 every 100, you would expect that after 100 times we would get at least 1, right? So that's kind of like the idea that the expectation is 1 over P. Okay, so if I use this notion of geometric random variable for my Cooper collector problem, then I can define the problem is easier that way, and that's how we're going to solve it. So instead of like saying that the probability of collecting all of them, I'm going to define this T1 to T5. These are different geometric variables. T1 is the probability of finding the first coupon. T2 is probability of finding the second coupon after finding the first coupon, and so on and so forth. So I define it this way. And essentially, by the time I get to this one, I collected all the coupons. In fact, there is proof that you can essentially, the probability of finding all of them, or expectation of T, E of T, is equal to E of T1 plus E of T2 plus E of T3, and so on and so forth. So in fact, and then if I actually plug in the numbers, what's the probability of finding the first coupon is n over n, because the first one I bought, definitely you're going to get a coupon. The second one, the probability is n minus 1 over n. So as I said, the expectation would be 1 over that. So it would be n over n minus 1, and so on and so forth. The second one would be n minus 2. So actually, if I plug in the numbers, I'm going to have a harmonic series, for those of you who remember the series. But it would be basically n times the harmonic series. If you don't know what it is, just the answer, this is approximately n log 2 of n. Okay, so going back to the example, if I plug in 5, would be n log n2 of 5, which is 12 something.
It's 11.6.
Okay, so 11.6. That's how we come up with like number 12. Was that the math that you used?
Yeah.
Okay, cool. Good job. Anyone has any questions here? So we're pivoting from computer architecture, which is good for you. Sometimes, math is helping you. But going back to the cache side channel problem, remember I told you that how many addresses do I need to have in order to access this? It basically becomes the same problem as the one we described in the birthday paradox. The analogy is that these are the birthdays and we want to have a collision, right? So you can actually plug in the numbers for number of sets. And in fact, for example, for a 8 megabyte 16-way cache with 8,192, only 42% of the cache needs to be installed, needs to be analyzed. This is equivalent of around 20 seconds. So in 20 seconds, we can actually find a conflict, a collision. On average, of course, it may take more for different systems if you're unlucky, but in 20 seconds I can find a collision. So what we were doing before, so we are trying to make it harder for the adversary to find these collisions. We show that okay, if I do the mapping differently, I can basically make it harder. But again, it's not that hard. Okay, so how do we do to make it better? If I actually can change the mapping before this 22nd, then I'm golden, right? So then I'm safe, because essentially by the time that the adversary can find the mapping, I've already changed it. Okay, so that's the basic idea of this attack, this defense. So think about it this way: that I have a cache with 2 ways and multiple sets. There is this pointer that they've defined. Essentially, wherever the pointer is pointing, this is where the mapping happens. Once the pointer goes to the next one, then I need to map everything above it. So in this case, I need to remap A0 and B0. So in this case, I map these 2 guys to here. And then this red means that these lines has been mapped. You got a question?
So essentially, like you're flushing your cache every 20 seconds.
So that's one thing you can do. But these guys are introducing the idea of gradual. So that's why they're not flushing the cache so after some number of accesses, so I think they have 200 accesses. After 200 accesses, they remap only 1 set and they go to the next set. So by the time they get to the 800 accesses, everything has been remapped. And that's what they kind of define.
Save on performance by instead of flush, you just move.
You just move,
So
yes.
the data is still there, so you're not going to lose out on performance then?
You're gonna lose a little bit of performance because of the locality. Because in the past you had locality and now things are scattered all over. But essentially your data is still there, so you're not.
But also another question then,
Mhm.
so it's like, it's just kind of like probabilistic, right? It's like, okay, it normally takes this long to
Yeah.
find it. But like, what if you find it faster?
Yes,
And
then
you-
you're,
But the thing is, you only need to attack it once to find it faster, right? Like,
yes, so this is a probabilistic defense, it's not an absolute defense.
but I think if you're an attacker, you can just try it a bunch of times until you get it faster.
But this constantly also changing, right? So again, this is just on average, you are not safer than this. And then again, another thing, so you can actually be very aggressive with this number of accesses. So they have like proof and all for their attacks. By the way, this is they published this in 2018, then they published an attack to their paper in 2019 and so on. So there is like an actually ongoing thing. But you can, again, this does not give you guarantees. It just gives you that on average you have this this protection.
Infinite research paper glitch.
But it works actually, because again, so you can say that there is a possibility, but again, we are arguing that probability is very, very small, especially if this number is very, very small. But yeah, but same as, for example, like our encryption mechanisms are not 100%. There is, for example, hash functions. It's not like impossible to find 2 hash functions that have collision. It's very, very low, the probability. It's like 1/2 to the power minus 64 or something. So it's same idea. How do I access? Then since I'm kind of moving things around, I need to also kind of somehow remember what I moved. So the idea that the authors had was like, you remember kind of the key that you use. So you kind of augment each part of like each cell of the cache with the ID that you use. So they use this notion of what they call epoch ID. which essentially like these fours are epoch ID 0, this one is epoch ID 1. So you kind of remember which epoch ID you use, and then when you want to recover the data, you just use that. So essentially you can think about it that before the pointer, use the old key, after the pointer, use the new key, and then each one has the epoch ID as well. And that way you can actually read. This will obviously, first of all, the main trade-off is not every axis needs to go through a decryption encryption that adds cycles. They show that, for example, the encryption decryption is very fast within one cycle. So essentially they're adding like 1-2 cycles to 100 cycle axis. So it's only 1-3% of overhead added to the latency. But then you also need to kind of store these epoch IDs and all that. So there is these trade-offs that one needs to be worried about. But if you're interested, definitely go and read the paper. Let me see if I put the paper. Yeah, the paper is here. Yeah, it was somewhere here. Yeah. So this is a good paper. All right. So that was randomization and a little bit of some other topics that was not relevant, but good for you to know. So what is other solutions? Another solution is detecting things, okay, and monitoring, as we discussed. The key idea in the monitoring is that the attack has some form of a repeating pattern, some behaviorals that you can expect that things happen. There are two classes of detections. One is rule-based. The idea of rule-based is that if I randomize the addresses, if this access pattern is indeed random, then it should stay random. So it's like the pattern shouldn't change. But if the access pattern is not random, it's like directed by the attacker, then if I change the patterns, I'm going to just basically see the same pattern over and over again. They call it like replay, record and replay. So essentially, they just change the mapping and say that, oh, the attacker still tries to access now another set of addresses, but again, they're very close to each other and so on and so forth. Another thing that people have found is like, okay, good old machine learning based techniques. I feed the addresses to some form of anomaly detector, try to see if I see any sort of patterns. People have published papers there as well. Any other solutions you want? Yeah.
A question about that. So let's say you're in like a data center, some sort of secure place, and you have the like ML detector and you detect something. What do you even do? Like okay, you're not 100% sure that they're like attacking, right? So like, but you can't see what their code is. That's like kind of like half the point, that you can't even see their code. So how do you even like deal with that?
So first of all, this detectors usually runs at the privilege level, so you can see what is their code. Because essentially you're assuming that the user level is the one that's attacking your system. So you should be able to see.
But I know sometimes on the cloud providers, they want like secure, like running your code securely. Like,
yeah, well, well, in that case, yeah, you just see the access pattern. Typically, these ML detectors are multi-layer defense, which means that then you kind of involve another more sophisticated defense that then look into, like, for example, another patterns. And then if all of them say that, yeah, there is something weird going on, then you can, for example, pause the application from moving forward, right? So the first thing, you can just kill the process if you're kind of unsure. And then worst case, they can just rerun the process, right? So for example, you can kill the process, say, okay, your process has been flagged because it's some unusual activity. Then you go and kind of tell them that, no, look, this is like some evidence that I'm doing something right. This is the reason. And then they allow you to rerun your application. So there could be these kind of like sort of mechanisms to allow you to kind of rerun. Actually, anomaly detection is quite common even in UCLA campus. If you start like, I don't do mining and all, you will be flagged. And you need to kind of like then you're going to be disconnected from the network, actually, or if you're running it in some form of a server. So there are actually already anomaly detectors like that. All right, so for all of these defenses, important things to remember is that there is overheads in terms of performance and area. There is some notion of accuracy. Not all of them are 100% accurate all the time. And there's also a notion of feasibility. In some cases, it's hard for your system to be feasible. Last thing I want to say before we have like 10 minutes. There's also another notion of attacks called covert channels. Did Fatima cover covert channels on Monday? No. All right. So covert channels is not between a victim and an attacker. It's actually between two attackers. They try to communicate to each other via the same measure that they launch a side channel. So for example, within the cache, they can talk to each other. Why they want to talk to each other? Because the regular channels, they cannot be able to talk to each other, because if they do, they will be caught. For example, many of you have done internships in companies that they encrypt all of your USB drives and thumb drives and all that. So if you're really interested in the file that you want to extract, what should you do? You can create a covert channel. So essentially you can extract the information from the laptop using some form of communication. For example, in the physical domain, there are lots of interesting covert channels. So for example, people show that if I can blink the hard drive LED and create some form of Morse code, right? Like 0, 1 blink, maybe 1, like 2 blinks or something like that. Then essentially, if I have a camera that records the blinking and then I write a code that basically detect the blinks and translate it into 0s and 1s, I can essentially extract any 0s and 1s I want, right? And this is one way of creating a covert channel. This is a physical way, but also think about the same way that we create covert channel for cache. So like, remember I told you that, I can basically do prime and probe, right? So the attacker do A. The victim was basically kicking something out and replace it with P, right? So now think about P is also attacker number 2. So if these two guys wants to communicate, they cannot share into the same drive, but what they can do is that they can agree on this thing, that if P wants to send 1, they're going to access the cache. If P wants to send 0, they're not going to access the cache, okay? In that case, A going to see two things. If it see A again, that means that the data that was supposed to be sent was 0. If it see P, then it sees it's a 1, right? So they can agree on this. They can agree on some form of a sampling rate. They can say that, okay, every 10 milliseconds, I'm going to do this. And they can send a lot of bits, actually. So this can be achieved like 100 kilobytes of data can be transferred this way. So the processes can talk to each other without anyone noticing, because essentially all they do is they're accessing their own data. They're just like, accessing their own data, they're mining their own business, but in fact, they're actually communicating to each other. And then think about that, for example, one process has access to the network, the other process has access to some form of a secret files. So the one that's basically extracting data from the secret files to the network, and the network one basically send it out, right? So there are a whole bunch of these attacks that can happen on the covert channel front, okay? This is basically breaking the least privilege principle. Remember, I told you that everyone has to have least amount of privileges. If one has some privilege that the other one don't, they can communicate to each other so that they have privilege of both applications. Okay. Yeah, for example, again, the other one process has access to secret but cannot communicate to outside. The other one can communicate to outside but does not have access to the secret. They communicate each other and then send things out. What are the defense against this? Some of the ideas that we shared with you can actually apply here. For example, if you make the setup more difficult, then the covert channel cannot also, has to be covert. The covert channel cannot also be set up. If we make a system more noisy, the covert channel cannot be set up. There are particular detection mechanism for covert channel that is slightly different than cache side channels, but generally they share similar ideas. Yeah.
Is it even worth like defending covert channels? Because I feel like there's like basically infinite covert channels.
Yes, covert channel is very, very difficult to detect, unfortunately.
Because you have because you have two systems, right? And you have one that's like looking for it. So it's not like it's like.
Yes. So they're colluding, unfortunately, which means much, much more difficult. Yeah. So it's much harder to detect. Yeah. All right. So to kind of summarize the what we discussed this week about attacks and defense, the kind of status quo for computer architecture and generally for our systems is that for the longest time, we didn't really care about these things. And that's what's actually fundamentally the reason that we have these problems. Though we didn't really design for security. We didn't think about that all things can be shared and sharing could result into these problems. All of these things that we discussed in this week was actually all happens way after the fact that cache is being used. Cache has been used for 20 years, and then later people figure out these kind of attacks. And the reason for that was that we didn't have the knowledge and we didn't care for that. And then, of course, now that these attacks are so widespread, then it's kind of like now we are realizing that what we should do. And then the fundamental reason for this is we want resource sharing, we want contention for efficiency, for power consumptions. It's not like, oh, we didn't want resource contention and now the attacker is using it, so let's actually disable it. Actually, if I disable, for example, cache sharing, the performance is going to be immediately terrible. So nobody even today is disabling any cache. They're still sharing cache and all that. But unfortunately, for the very same reason, we are seeing all these problems with security. What is our current strategy? Our current strategy is whack-a-mole. So that's what we do. All of the companies are basically doing this. So a new attack happens. They figure out some form of a patch, fix it, and then another attack comes in and so on and so forth, because there's essentially zero guarantee that you can fix these things because there's just fundamental reason of sharing is the key problem. So key takeaways for this week's, and you're going to actually see some good paper presentations in 2 weeks, is that unfortunately any shared resources can leak secrets. And then unfortunately these can be easily extracted through side channels. And what we need is effective defenses, more of a provable defenses that are secure by design. And these defenses needs to balance performance and security. That's the main thing. So you cannot just say that, oh, let's not use the cache or let's like aggressively partition the cache and all. We need to be very aware of the fact that, you know, we need to maintain the performance. What is a good answer? Almost nobody knows at the moment, but that's where the innovation can happen, right? So you can actually come up with very nice ideas. All right, so that's it for today. Next week, we're going to switch back to our just regular computer architecture. We're going to talk about backend.
Oh,
Backend.